All right. Hello, everyone. Welcome to our Mathematics Society and our Bluesat partnership. Welcome to the MATH2018 revision seminar. So I guess in our first seminar, this is what we're going to be going over. So I suppose we'll just start off with the first topic, which is functions of several variables. So the first thing that we really are introduced to when it comes to functions of several variables is the idea of partial derivatives, right? We're extending this idea of normal derivatives into multivariable functions. And here we have an example question from a past paper. So we've got a function, z equals f of xy, given by x squared y cubed plus e to the 4x sine y. So now what the question's asking is f an increasing or decreasing function in the direction of x at the point 0, pi on 2? So when we want to talk about whether a function is increasing in a certain direction or decreasing in a certain direction, we need to take partial derivatives, right? Because a partial derivative is going to tell us that. So, and it's in the x direction, so we obviously take the partial derivative with respect to x. So we'll go df on dx is going to be equal to 2xy cubed plus 4e to the 4x, sine y. So here we go, partial derivative. Now that we have this partial derivative, we want to see whether it's increasing or decreasing in that direction. So the way we do that is we simply plug in the point that we're given. We plug in the point 0, pi on 2. So if we plug in, or if we evaluate, df on dx at 0, pi on 2, we simply just get 2 times 0, pi on 2 cubed plus 4e to the 0 sine pi on 2. Now we'll see that the first term, obviously we're multiplying by 0, whole thing goes to 0 there. And then our second term, we just have 4e to the 0 sine pi on 2. Sine pi on 2 is just 1. E to the 0 is also 1. So we get that our partial derivative is equal to 4 at that point. So what we can deduce is that the function must be increasing in the x direction at that point, because we took partial derivative with respect to x, and we plug in the point, and it was positive. So therefore, it's increasing. So pretty straightforward forward example. So now we extend this idea of partial derivatives, and we go a little bit further, and we look at a thing called the multivariable chain rule. So suppose that we've got a whole series of functions here, right? We've got u is x squared plus 4y, but then we also have that x is a function of s and t, and that y is a function of s and t as well. So it's, I don't know, it's a bit like Inception. We just have all these functions with variables nested inside. And we want to evaluate these derivatives, du on dt and du on ds. Which, lucky for us, we have a rule for this, and it's the multivariable chain rule. So it's this, right? So if we've got z is some function of x and y, and then we have x and y are functions of separate variables, that being like u and v, or in this case, s and t, we can simply just evaluate these derivatives using this multivariable chain rule. And it's very similar. You'll notice that it's very similar to the regular chain rule for single variable functions, but instead we've got like an extra, we've got an extra term here, right? And that's simply because we have to account for both the x and the y variables. So what we'll do is to evaluate du on dt, we'll say that, partial So we can write this as du dt, and we put our first variable in, and then we have our second variable. So if we want to evaluate this expression, obviously we have to evaluate du on dx, and we need du on dy. So that's the first thing that we do. So we get du on dx, we get du on dy. And we get these two functions as shown here. And looking back at our formula, we also need to get this and this. We need our dx dt and our dy dt. So we'll go ahead and evaluate those. So dx dt is going to be d on dt of 3st, which is just 3s. And then dy on dt is just d on dt of 4s ln t, which just gives us 4s on t. And now what we can do is we can take these respective terms, du dx, as well as our dx dt, multiply them together, and we do the same thing for the y. And we end up, for our du dt, we get our 2x, because that was our du dx, times our 3s, which was our dx dt. And then we take our du dy, which is just 4, and we multiply it by our dy dt, which gives us 4s on t. So we end up with this expression like this. We get 6xs plus 16st. Now, since we're differentiating, like if we look at the question, the variables that we are differentiating with respect to is t and s. But you'll notice that we've got an x in here, which is not very nice. We don't really want that in there. But lucky for us, we have x as a function of st. So we simply just plug that in. So since t and s are our inputs, we replace x with 3st. So when we plug that in, we end up getting 18s squared t plus 16st. And this here is our du on dt. So we've evaluated this part. Now, for the sake of time, right, it's the same process to get du ds. It's simply just going to be du dx, dx ds, and then the same for the y value. So it's just the same process that we've done, and then we plug in our s and t values back in to get rid of our x's and y's. So yeah, we just do the same thing with du ds. It's the same process. We're evaluating our du dx, dx ds, du dy, dy ds. So we're just doing that, and then we end up again with an expression similar to the last one that we got. And then since we want to get rid of x, we want to express everything as s and t, we simply just plug in our x, which is our function up here. And then we end up with this. We end up with this final expression. So we can then say, now that we've evaluated du dt and du ds, we can therefore arrive at this conclusion. So we have this. So again, fairly standard question. It's just a matter of knowing what the multivariable chain rule is and just applying it. So now we move on to the next concept, which is Taylor series, right? And this you would have learnt in Math 1B, and we often see the Taylor series expressed as this, right? Or I guess in a more concise form, we get something. So we're used to seeing our Taylor series like this. And this is for single variable functions. This is for functions that map from R to R. But now that we're looking at multivariable calculus, we have to now account for this. Well, what if we have, instead of just x, we've got x and y? So lucky for us, or I guess unlucky for us, it's a pretty yuck formula. But we have a way of determining some kind of polynomial approximation for these strange curves that we have in three-dimensional space. So I guess intuitively the idea behind this is that we want the derivatives to match up, we want the function values to match up at the point. If we're approximating the curve at that point using some kind of polynomial in x and y, the function values have to match, or else it's going to be a terrible approximation, right? Additionally, we want the x derivatives and the y derivatives, these first order ones, to match up at the point. And then we want the second order derivatives to match up. So then we look at d squared f dx squared, and we look at all these permutations of second order derivatives that we can put in there and make sure that those match up. And then obviously we can extend this to third order, fourth order, and make them all match up, but in this course, we only need to go up to second degree terms, because otherwise we get a huge mess and it's just terrible. So we'll consider this question, right? So we want to construct a Taylor series up to the quadratic terms. So we're only considering first order and second order derivatives of the function f of x, y is sine x cos y, about the point x, y is pi on 4, pi on 2. So if we look at our Taylor series, the first term that we're worrying about is, okay, f of ab. We want to make sure that f of ab lines up. So we need to assign a function value there. So we'll say, well, we'll evaluate f of ab, and we'll say this is f of pi on 4, pi on 2, which is simply sine pi on 4 cos pi on 2. Sine pi on 4 is just 1 on root 2, and then cos pi on 2 just goes to 0. So this whole thing's 0. So we'll just say this is equal to 0. Okay, that's quite nice. We've got one less term to worry about. So yeah, we plug that in, we get 0 for our initial term. So now we have to consider the first order partial derivatives. Yeah, so we'll calculate those. So we'll say that df on dx is going to be, so our x term in our function is just the sine x. So we want to differentiate sine x, and that goes to cos x. So we get cos x, and then the cos y remains unchanged. So then we can say, well, at pi on 4, pi on 2, pi on 4, pi on 2, df on dx, and you'll notice because we have cos y again, and our y value is pi on 2, cos pi on 2 is just 0. So this whole thing goes to 0 as well. So this is 0. Now we evaluate our other first order partial derivative, which is going to be with respect to y. df dy is going to be, so we take our y term in here, which is the cos y, and we just differentiate that and leave the x term. So the cos y has been going to become a negative sine y. So we get sine pi on 4, sine pi on 2. So sine pi on 2 is just 1. If we just think about a sine graph, it'll be 1. And sine pi on 4 is going to be 1 on root 2. So this is just going to be 1 times negative 1 on root 2, which is equals, and I should say that this is at pi on 4, pi on 2. So we've got that our partial derivative with respect to y is, and there is a negative sign on there, negative 1 on root 2. So we've finally actually got a term in our Taylor series. Okay, sweet. So we've evaluated our first order partial derivatives, and we plugged our values, and we get 0 and we get 1 on root 2 respectively. So now we have to calculate second order partial derivatives. So I won't go through that because that's going to take a while. But yeah, we'll recognize that anytime we have a cos y, it's always going to be 0 because cos pi on 2 is always 0. So that means that d squared f on dx squared goes to 0, as does d squared f on dy squared. That also goes to 0. And we'll see that the mixed partial derivative gives us the same thing that we had for our df on dy. So we get another negative 1 on root 2. So if we look back at our Taylor series formula, we can say, oh, well, this here is 0. This here is negative 1 on root 2. This here is 0. Whole thing goes to 0. This thing here is also 0. So that whole thing cancels. Really nice, right? And then this term here is our negative 1 on root 2. X minus a value was our pi on 2. Oh, sorry, other way around. X minus pi on 4. Y minus pi on 2. And then it's really nice because we have a 2 here, which also cancels with the 2 here. So we end up getting really just this term of our polynomial and this term of our polynomial. So it's really just our Taylor series approximation is just two terms, which if we go down here, again, this is just like a recap of what our derivatives are. We plug it into the formula and we get this. This is our Taylor series approximation. And granted, it doesn't look very nice because we got a lot of fractions and square roots and stuff. But when we look at the graph, this is what our approximation looks like. So the gray graph is the original function, sine x cos y. And then this red function is our Taylor series approximation. So it's a bit hard to see, but it like just comes down and touches it, and then it passes through. So we can see that locally we have an all right approximation. So that's how we do a simple Taylor series question. The hardest bit of these questions is just remembering the formula. It's a bit of a long one, but yeah, that's pretty much the gist of Taylor series. So now we move on to an application of these ways to approximate our functions, and we look at error approximations. So a very, very standard question that you're going to get given when being asked to approximate the error is something like this. So we have the volume V of a cone with radius r, perpendicular height h is given by the volume of a cone. And we want to determine the maximum absolute error and the maximum percentage error in calculating V given a value for r and h to the nearest millimeter. Now, before we jump straight into this, we want to know, okay, how do we actually do this? So the way that we do this is we use this formula. We have a nice formula that tells us the maximum error, and it's given by this. And you can sort of see, if you're quite observant, it's very reminiscent of the triangle inequality. But delta x is going to be our discrepancy, or our, I guess our error in one of our values. For instance, it might be r, and then like delta y might be like the leeway or the error in like h. And then we can just use that to calculate what the maximum absolute error is going to be. So it's a pretty neat formula, and it's a very, very easy one to apply. So we'll go, whoops. So we have the, let me get the problem up. So to work this out, we're going to say that v, our function, is given by 1/3 pi r cubed h. Was pi r? Oh, it might have been pi r squared h. Pi r squared h. Yep. Sorry, my bad. Pi r squared h, and we know that the change in, or the absolute error in v is going to be okay. So we've got this. This is just by applying this formula. So instead of x, we write r, instead of y, we write h, and then instead of f, we're obviously calculating v. So the first thing that we're going to do is we're going to evaluate these partial derivatives. So we're going to find dv on dr, and that's just a simple application of partial derivatives. So this will become 2 pi r h on 3. And then we get dv on dh. Since the h is just it's just by itself, we can just drop that. So we get pi r squared on 3. Okay. So if we look down here, that's same partial derivatives. Now, the next question you're probably asking is, okay, what's our delta r? What's our delta h? So, got a bunch of, yeah, here we go. What's delta r? What's delta h? Now, in the question, it said to the nearest millimeter. I guess if you guys have taken like a physics course, I mean, this is an engineering course, so I'd assume most of you guys have taken first year physics. When we look at like discrepancies and like inaccuracies on like a device, and we want to find what's the maximum error, it's usually half of the smallest unit of measurement. So in this case, if we're going to the nearest millimeter, we take half of that unit of measurement. So it'd be 0.5 millimeters. So in other words, that's what our delta R is, and that's what our delta H is. Obviously, if we're measuring the radius in centimeters, or I guess in millimeters, and we're measuring the height in millimeters, this is going to be our maximum discrepancy. So, and since our values are given in centimeters, we have to convert to centimeters. And then so these are going to be the same. So now it's just a matter of plugging in our values that we're given. So we're given that the radius is 5, and we're given that the height is 3. So we plug that into our, this here is our dV on dr, and we're evaluating this at 5, 3. And then obviously we multiply by the uncertainty in R, which is our 0.05, which we got from the last slide. And then we do the same thing. We just take, this is our partial derivative here, dV on dH, and we're evaluating it at 5, 3. So I'll save you guys the calculations. We have it up there, so that we get that the maximum error is this right here. It's 2.87. So we've found what the maximum error is, but they ask for the maximum error percentage as well. So we can't just neglect this. So the way that we do that is the percentage error, we just take our uncertainty in our volume and we divide it by our volume. Because this will give us what percentage of the volume is our uncertainty. So we get just the absolute value of delta V over V. And the way that we get V is we just take the volume, which we had said was 1/3 pi r squared h, and then we just evaluate this when the radius is 5 and the height is 3. So that's how we get this value here. And then that 2.87 is what we just calculated. So we divide it to get the percentage. So we have a percentage error of about 3.65%. So hopefully that makes sense. It's fairly simple question. Again, it's just a matter of knowing the formula, knowing what it's asking you, and just plugging numbers in. So now the next thing that we look at is the Leibniz rule. And this is it's a pretty daunting formula to look at first. Quite a tricky one to remember. But what this allows us to do is very, very powerful tool. We can take some integral, and we can differentiate this integral. So I guess we differentiate, and then we oftentimes get a nicer integral. So we'll have some other integral that is usually nicer, or it'll be some kind of information that we can use that allows us to work that out. And then we also get these additional terms here, because it would be, it would be too good to be true if we can just differentiate it and then it's just the partial derivative. That would be too great, right? So obviously we have to have these extra terms tacked on the end. So yeah, so this formula is giving us a way to take an integral and differentiate it, which is something that we haven't known how to do beforehand. And what makes this tricky is that there's a lot of sources of change in this integral. There's a lot of things that will make the values different. Like if f, the actual function inside the integral is changing, like if it increases, then our integral increases. And then since our bounds here are functions themselves, if we start varying those in our integrals, everything's changing, right? It's really weird. So we sort of account for that with this little term. Well, not very little, but we account for this with this term at the end. Now, going back to what I said about it being too good to be true, there actually is a case where we get a very nice result, and that's when Vx and Ux are constant. So, yeah, so I'll write an explanation as to why this is the case. So if we have, technical difficulties. Yeah, so suppose we have an integral like this. And this is with, I'll just use the one that, so they differentiated with respect to x, my bad. Let's change this to an x. dt. Now using the formula above, I'm just going to write directly what they have. And then we get these weird terms on the end. So we get f of x vx, v dash x. And then we subtract f of x, u of x, u dash x. Now, the case where this is really nice is when u and v are constants. So if u is a constant, its derivative is 0. So in other words, if u and v are constant, it follows that u dash equals v dash equals 0. So they're both equal to 0. So what that means is that if we have constants, this whole term and this whole term get wiped out. So we're left with this really nice integral property that, a really nice case of the Leibniz rule. So, whoops, doesn't seem to like me. So we get this really nice property. df on dx xt dt. And this is, of course, only if our bounds are constants. Otherwise, we have to include the mess on the end of it, which is, I'm not a fan of it, but, you know, it's just a fact of life. That's just how it is. So yeah, this is what we just looked at. So if we have a and b constants, then we can simply just take the derivative out the front and move it inside the integral, and it becomes a partial derivative. So that's enough of me talking about this rule. Let's actually use it. So we have this integral here. We want to find the derivative of the integral from 1 on x, 1 to x of 1 over t squared plus 1. So what we do is we apply the Leibniz rule term by term. So we want to recall that we can move the partial derivative inside the integral. That's the first step. So d on dx, d on dx, x to 1 is equal to, so our first term we just move the partial derivative in. This is okay, so what do you guys think this is equal to? If I take the partial derivative of what's inside with respect to x, what do I get? Yeah, I just get 0, right? So this is the first term. Oh, okay, this is just 0. How convenient. So that integral just disappears completely. Okay, so now we don't have to worry about doing any more integration. And then the next term we want to add is our f of let me make sure I get this right. F of x 1, and I'll put 1 in red. What is happening? Yeah, I'll put 1 in red because this is the integral bound that we're subbing in. And then recall that we need to take the derivative of the bound that we sub in. So this will be d on dx of 1. And what's this equal to? This is just 0 again, right? Oh, that's even more convenient. Oh, okay, so we just have another term that goes to 0. Okay, well then we'll sub in the last term. The last term is going to be minus, oh, it's going all over the place. So our last term is just going to be minus f of x, and then we sub in our bound, f of x, and then we just have like dx on dx, which is just 1. Okay, so we've got a term that doesn't go to 0. Okay. And then f of x, well, since our function, like f of xt, is just 1 on t squared plus 1, we just replace the t with an x. Because our t variable in here is getting replaced with an x in our function. So this is just going to be equal to negative 1 on x squared plus 1. Which we end up with that. Now, if you're pretty observant and you look at this question, you'll come to realize that we don't even need Leibniz rule for this. But we're going to do the actual integration just to check and verify that our answer is correct. So we can evaluate the integral by itself. This is a standard integral. I'm sure all of you guys know how to do this one. This is just going to be tan inverse t, x to 1, so we just get pi on 4 minus tan inverse t, and then, oh sorry, it should be tan inverse x, my bad. Whoops. Tan inverse x. And now if we just differentiate this with respect to x, we just get negative 1 on x squared plus 1. Which, I mean, we could have done that in the first place, but it's good to see how this rule works, and it's good to be able to apply this. So now we're going to try a harder question, one that's not so trivial. So we're given an integral. A lot of Leibniz rule questions are going to be like, given this integral is equal to this, what's this other integral equal to? And it's usually always going to be, we can just differentiate it using Leibniz rule. So I guess we'll try and go through this quickly. So the idea of what we're trying to do is we're trying to transform this into this. And the way we do that is we have to use some kind of operation. And that's what Leibniz rule is for. So so we want to decrease the power. And we do that by differentiating. So we move the derivative inside the integral. We differentiate both sides. The sinh inverse 1 just goes to 0. And then this goes inside the integral. So we end up getting, we move the partial derivative inside, and then we get this additional term that we have to tack on the end, because you'll notice that our limits of integration are technically functions, because a is a variable. So when we simplify this partial derivative here, we end up with a negative a out the front, and we've got the integral that we're looking for. And we know that this is equal to 0. So we can simply just move this over to the other side, was of course using the fact that this is 0. And we end up with this simplified expression. If we move the integral over, and then we just divide through by a. So this will become an a squared. And then since we're moving this over, it'll become positive. So this integral will just be 1 over root 2 a squared. And we're done, right? Bit blitzing through that a little, but we just simply differentiate and use the fact that it's equal to 0. We use the part that they'd given us, and then happy days. We don't actually really have to do any integration at all. So that wraps up functions of several variables. So we'll move on to extreme values. So critical points, we've seen this in functions R to R. It's just when our derivative is 0. We see this as stationary points, points of inflection, like horizontal points of inflection. We've seen all this in high school, right? And we sort of draw an analogy, or it's the analogous version of that in R2 functions is we look at our partial derivatives and we see how they behave, right? So much like our single variable functions, we have the multivariable equivalents. We have local mins, local max, and we have saddle points as a new kind of point, right? And the way that we can find these is we define this expression here. So we have this expression involving partial derivatives. And if you're interested, this is something that we call, a fancy name is the Hessian determinant, or the determinant of the Hessian matrix. It's a fancy name, but you can just remember this. And we have a criteria or a way to classify these points. So we say that this expression that we have at the top, if it's positive, that's the first part, if it's positive, then if the second order partial derivative with respect to x is negative, then it's a local maximum. We can sort of think of this second derivative, it's sort of similar to concavity, and if concavity is negative, it's pointing down, so it means that we're up the top. So it'd be a maximum point. And then likewise, if d is positive again, and our partial derivative is positive, our second order one, it's sort of going upwards, so it's a local min. And then we say that if the expression at the start, this big partial derivative thing we have here is negative, then we've got a saddle point. And if it's neither, it's 0, then our test doesn't really work, and we sort of have to deduce, using logic, what does this shape look like, etc. So we'll take this graph, h of xy, and we want to provide the function value at the critical points. So to find critical points, the way we do that is we evaluate our partial derivatives and find when they're equal to 0. So partial derivative with respect to x is just going to be, this term will become 6x squared, then we get 6xy, and these terms just disappear. So we end up with this. We get this nice expression here. And then, again, with respect to y, we just get 3x squared plus 2y minus 1. So we get this. And then we want to evaluate when these are equal to 0. The way we do that is we can factorize. So we can factorize this equation to give 6x outside of x plus y equals 0, which same as saying x plus y equals 0. And then we have two cases, right? Either x is 0 or x is negative y. So, yep, our first case, x could be 0. So then we can substitute that into our second equation, which is this one here. We can make this term 0. So then we'd end up with the x term would disappear, so we're just left with a 2y minus 1 is 0. So then from that, we get y is a half. So we get a y value out of that. Alternatively, we have another case to consider, and that's when x is negative y. So if we again plug that into our second equation, we can get a quadratic in terms of y, purely in terms of y. And then this is now just a simple solve a quadratic equation. We all know how to do this. And then we get two cases for y. And this is, of course, when x is negative y. So x would be the corresponding value. That's just, you just take the negative of whatever this is, and that's your corresponding x value. So now we've found our critical points, but we don't know what these points are. We don't know if it's a saddle, we don't know if it's a max or a min. So that's when we bring our second order partial derivatives in here, and we use that criteria that we saw earlier. So we can evaluate the second order x partial derivative, and we get 12x plus 6y. We can evaluate it with the second order partial derivative with respect to y, and we just get 2. And then if we do the mixed partial derivative, we get 6x. So now when we plug that into our expression that we had before, which was the second order x and y partial derivatives multiplied together minus the mixed partial squared, we end up getting an expression like this. And what we can do is we can plug in our points. We can plug in those critical values that we just found. And when we plug in x is 0, y equals a half, which was the first one we looked at, we get that our expression d, we'll just call it d, is equal to 6. So it's greater than 0. Okay, sweet. And then we check the x partial derivative, and that's equal to 3. So that's positive. So d is positive, second order x partial derivative is positive. That means that we've got a local minimum. So just using that criteria that we'd seen earlier. So we've got a local minimum there. And then now we just plug in our other points. So we have negative 1 on third, 1 on third. That is when x is negative y. We get a negative d. So immediately we can say, okay, well, if it's negative, it's a saddle point. Done. We don't have to do any further classification. It's really nice. and then, and then we plug in the other possible xy value, which was y equals 1, or y equals -1, x equals +1. We sub that into D, and it's less than 0, so that means that we have another saddle point. No more further classification required. So all we need to do now is find the function values. And the way we do that is we have h of x, y, we have our 3 coordinates, so it's just a matter of plugging it into the equation, which is something that it's fairly straightforward. You just punch the numbers in your calculator and it'll give you the values. So subbing these in at 0, 1 at our local min, we have a function value of -1 on 4. At our first saddle point, -1/3, 1/3, we've got a function value of -5 on 27. And then at 1, -1, we've got a function value of +1. And that's our other saddle point. So what we've done is we've found the critical points, we've classified them, and we found the function value. So we sort of have a good idea as to what's happening with this function. Now, one of the trickier parts of this extreme value thing is Lagrange multipliers. And it takes this concept that we're used to in high school of like minimization and maximization, and now we have to account for multiple variables all at the same time. So a very typical question is, suppose that the surface area is given by 50 centimeters squared. So what this is we have some kind of constraint. So we've got a constraint, and then we want to find what's the maximum possible volume given this constraint. I am not very good at spelling either. Constraint. No one called me out on that. So we've got a constraint and we want to try and maximize our volume so that it lines up and agrees with this constraint. So we introduce this wonderful thing called Lagrange multipliers, which, in order to understand what a Lagrange multiplier is, we have to introduce this thing called nabla, which is this upside down triangle. So it's this fancy term, differential vector operator. And what that means is that we just slap it onto the front of a function, and it takes that function and it turns it into a vector. And all we do is that the x component is the partial derivative with respect to x. The y component is the partial derivative with respect to y. The z component, you sort of see where I'm going, et cetera, et cetera. So we can just think of it as the collection of partial derivatives of the first order just in vector form. So we end up using this. We can construct an equation. I won't go over like why the geometry of why this stuff works, because that will take a while and we don't really have time for that. But we can construct this equation that, given some constraint, this is one of our equations that we have to account for. We can say that nabla of f is equal to lambda nabla of g, where g is our constraint. So this will give us a system of equations that we can solve. And oftentimes we want to eliminate lambda as a parameter. Like we'll typically have two equations, and we get lambda equals something, equate the two, find a relationship between them, sub it into the constraint. So that's, I guess, the spark notes of how to do this. So yeah, we'll end up getting a system of simultaneous equations, which is sort of to be expected. So, and the really nice thing about this is we don't have to worry about the nature of the critical points. Since we're worrying about how to maximize something or minimize something, the larger value is going to be the maximum, and the smaller value is going to be the minimum. Like, it's fairly logical in that sense. So here's very typical question. So suppose that we have the surface area of a cylinder with a base but no lid. That's very important, no lid. And it's 16 centimeters squared. So we want to find the... Oh, let me just grab that. Yeah, so we want to find what the maximum possible volume of this is going to be. So we want to, turn this into an actual maths. We want to turn this into maths, right? Introduce some numbers. So we've got our cylinder. It has a radius r and a height of h. Yep, so we just define it to be that. Now, we know that the surface area has to be 16 centimeters squared, but the surface area doesn't account for the lid. So there's no lid on the top. So we add the base, the area of the base. Surface area is going to be pi r squared plus 2 pi r h. So this will give us the area of the side of the cylinder and then the base of it. And then we know that the volume is pi r squared h. So in other words, we're trying to maximize our function, which is the volume. So we'll say that f of RH is pi r squared h. So this is our volume. So we're maximizing the volume on the constraint being our surface area. I'll say surface area. So now we can apply our method of Lagrange multipliers. So what we do is, given that the equation for Lagrange multipliers, this is our equation that we're trying to solve. So obviously we just take nabla of f, nabla of g. So f is pi r squared h. F so that means that nabla f is df dr df dh. So we end up with 2 pi r h. Oh, whoops. And we get pi r squared. And then if we do the same for g, which is our surface area, our constraint, we end up getting this. So this is our left-hand side and our right-hand side of the equation, respectively. So now it's just a matter of equating them. And since they're both vectors with 2 column entries, we can just evaluate the components separately. So that's where we get our system of simultaneous equations from. And of course, we want to put the lambda here. So the lambda is just because when you look at the actual geometry of it, nabla of f, that vector, is parallel to nabla of g. And if they're parallel, they're some scalar multiple of each other. So that's what the lambda is there for. So now we want to try and solve this equation, or this system of equations. And we want to get a relationship between r and h. And then we sub that into our constraint. So we evaluate the x components. So this is x components. This is y components. So then, so we factorize these equations as such, move it all to one side, bring out factors, and we end up with this pretty yucky expression. And we'll come to see that this actually, it doesn't really help us because we end up with just a lot of trivial solutions. So the better way to go about doing this is we want to get lambda as the subject in both equations. So we'll take these equations that we have here, and we want to get lambda as the subject. So I'll just go through how we get that. So if we have RH minus lambda equals 0, lambda so that's our first equation. And then this one here, I'm sure you can just do in your head. You move it to one side, divide by 2, lambda is r on 2. So we have these two equations, two expressions for lambda. We got this and this. Now, since lambda it's a yucky variable, we don't want it, we just toss it out. And the way we do that is we just equate these expressions because they're both equal to lambda. So we equate it and we get RH over r plus h is equal to r squared. And then just by a bit of simplifying, I'll do this. So we get cross multiply, we get this. And then subtract this over. Therefore, r equals h. So now we've finally got this relationship between the radius and the height. Now the last step is we sub it into some equation where there's some value that we know, and that's what our constraint is. So we take r as h, and then we sub it into the constraint equation, which was the surface area. By doing that, we end up with, we end up getting this expression. We end up getting 3h squared is equal to 16. And then it's just a matter of dividing both sides by 3, square rooting, and then we get that the height is going to be 4 over root 3. So all we've done is, just a quick recap, we've got both equations in terms of lambda, or we've got lambda as lambda equals something for both equations. Then we equate the two to get rid of lambda, because lambda's not helping us with anything. And then we sub in that relationship, or we end up with a relationship between r and h, and then we sub that into the constraint. And then we get some kind of value, like h equals 4 on root 3. And then we use that relationship, that h is equal to r, to deduce that r is also 4 on root 3. Ooh. Now to find the volume, or the maximized volume, we simply just plug it in. Yes, because we only got one critical point. So that means that whatever it is, it's going to be our max. Happy days. So we just plug that in, and we end up getting 128 pi over 3 root 3. So fairly straightforward Lagrange multiplier question, fairly typical. So yeah. Now matrices. This topic, matrices, is quite difficult. It's quite abstract. It's a lot of theorems and things to memorize. But we'll start off with a simple question. We're told that a matrix is diagonalizable, has eigenvalues -2 and 1. Now there's two things the question's asking us. Verify that 2, 1, 1 is an eigenvector, and then hence diagonalize the matrix. Okay. So the way to verify that 2, 1, 1 is an eigenvector is we use the eigenvector equation. So we'll say that, so if V is an eigenvector, then we have some value lambda, such that when we multiply the matrix, it just scales the vector. So to determine whether this is actually an eigenvector is all we do to take this matrix, multiply it by this vector. If the resultant vector is a scalar multiple of this thing here, then it's an eigenvector, just by this equation here. So, that's a bit, whatever, it'll be fine. So yeah, this is the equation that we've just looked at. So we multiply a by the vector. So doing so, I'll save you all of the matrix multiplication. It's quite tedious, but we end up getting -2 times this vector. So it's scaled it, hasn't rotated or anything, hasn't knocked it off its span. It's just scaled it by -2. So what that means is that not only is it an eigenvector, but it has an eigenvalue of -2. Now, the next part wants us to diagonalize the matrix. So the way we diagonalize is we find eigenvectors and we find eigenvalues. Now, the thing that you'll probably notice is that we've only been given 2 eigenvalues, right? And the way that we normally find them is we calculate the characteristic polynomial, find the roots of it, all this horrific algebra that no one really wants to do. But there's a method or a thing that we can employ that will make our lives so much easier if we already know 2 of the eigenvalues. So first of all, we're not given a complete set of eigenvalues. That's the problem here. But lucky for us, for any matrix, for any square matrix, n by n, the trace of the matrix, that being the sum of the diagonals, so we sum these terms, That's what the trace is. The trace of the matrix is always equal to the sum of the eigenvalues. And that's for any square n by n matrix. So we've already given 2 eigenvalues. We know what the trace is. The matrix is right there. We can just do -5 plus 4 plus 1, right? Nothing too crazy. And we end up, when calculating it, we end up rearranging this equation to get lambda 3 is equal to 1. So that means that we have eigenvalues -2, 1, and 1. Okay, so we've got our eigenvalues, but we don't necessarily know what our eigenvectors are. We only know one eigenvector, and that was the one that we just shown was an eigenvector, which was this, 2, 1, 1. So we'll write this down, because this is very important. We need to know this. So V1 is 2, 1, 1. Lambda 1 is -2. Now, the eigenvalues that we have left are 1 and 1. So we have a repeated eigenvalue, which means that we have to, substitute this into the our eigenvector equation, and then by multiplying V by the identity matrix, by that, we can factorize it by bringing it over to one side. We get this. So now what we're looking for is the kernel of the linear transformation A minus I. So all we do is, it's just going to be our A matrix minus the identity matrix. So what we're doing is we're really just subtracting 1 off the diagonal in the matrix. So when we do that, we end up getting this matrix here. So again, I'll save you all the matrix computation because it's just very tedious, and it's stuff that it's fairly straightforward. So we get a matrix that looks like this, which is nice because a lot of things just cancel. We can row reduce it to just give us this matrix here. Whoops. To give us this matrix here. And then finding the kernel of this is very easy. So to find the kernel, it'll just be -1, 1, 0, 0, 0, 0, 0, 0, 0, times some arbitrary vector x, y, z, which is going to give us -x plus y, and then everything else is just going to be 0, which implies that x is equal to y. So we can get immediately one eigenvector. V2 is going to be 1, 1, 0. And then since, the thing you'll notice is that since this column here has 0 entries, if we wanted to do the matrix multiplication by saying it's x times the first column, y times the second column, z times the third column, it doesn't matter what we let z equal. Z can be anything and it will always go to 0. So in other words, if we just let x and y equal 0, but let z be anything, then we still technically have an eigenvector. So it's almost like a trivial solution, right? So V3, 0, 0, 1, this is also a part of the kernel. So this will always go to 0 if you multiply it by A minus I. So we've now got these eigenvectors. V is 1, 1, 0, and V is 0, 0, 1. So now, diagonalizing the matrix, this is what we're trying to get to. So the diagonal matrix is the one that just has non-zero terms in the diagonal. Like it's pretty obvious. If you see a diagonal, you'll know it when you see it. So to diagonalize it, we say that an n by n matrix is diagonalizable if there is some matrix Q such that we can write A as QD Q inverse. And D is the eigenvalue matrix. So this will be a 3 by 3 matrix, and the diagonal is going to be eigenvector 1, eigenvalue 1, eigenvalue 2, eigenvalue 3. And then our Q matrix is going to be the corresponding eigenvectors as the columns. And then obviously Q inverse is just going to, it'll be the same matrix, just the inverse of it. So we first find Q. So this here is our 3 eigenvectors that we calculated. So the first one we found by substituting in, and we saw that it just scaled it by -2. Sweet. So this has a lambda of lambda equals -2. This here was one that we found. It was in the kernel of a minus I. So this is going to be lambda equals 1. And then this here we also found to be in the kernel. So this is also lambda equals 1. So that means that if this is our eigenvector matrix, our corresponding eigenvalue matrix is going to be the corresponding eigenvalues across the diagonal, like that. And the order of this does matter. The eigenvalue in the first column has to be the eigenvalue for the first column of your eigenvector matrix. Like, it has to line up like it does here. So then we can simply diagonalize it by just writing it in this form, and we're done. That's it, we've diagonalized it. And that's all the question asks you to do. It doesn't ask you to do anything further with it. Now, one more useful application, I guess, of diagonalizing matrices is conics and quadrics. So quadrics is, we'll look at strange surfaces in, strange three-dimensional surfaces and what happens when we rotate them and trying to make sense of all this abstract geometry, right? So we can have some kind of graph that looks like this, and you might know, you might be able to visualize this as an ellipsoid. But that's because it's nice. It's just x squared, y squared, z squared. Like, it's nice to look at. We can easily visualize what this is. It's just a simple ellipsoid. But where it gets tricky is when we include terms like x, y, yz, and xz, because that means that we start rotating it around axes and it just gets all strange. So a way that we make sense of this is we use eigenvectors and eigenvalues. So say, for instance, we take a surface like this. Trying to visualize this, nightmare. I would have no idea where to start. But what we can do is we can redefine our set of axes to make this a much simpler surface to process and to actually understand what's happening. So for questions that relate that relate to conic and quadric surfaces, the method to solving this is we first want to express our curve, or express our shape, our surface, in the form x transpose, where x is just like the vector x, y, z, times some matrix A times the regular vector x, the non-transpose version, and it's equal to a constant. So in other words, we want to take this here and write it as, we want to try and express it in that form. And then this, of course, is our C. So one condition of this is that A must be symmetric. And this is very nice for us because it makes us a lot easier to work out what that matrix A is. And to get A, we simply do this by, we can simply do it by observation, right? And once we found A, we then find the eigenvalues and the eigenvectors of them. And once we've done that, we diagonalize it, like what we just did before. But the catch here is that Q must be orthogonal, must be an orthogonal matrix. Once we've done that, we can redefine a new set of axes in the form x is Q transpose times this position vector x. And it'll transform into a much, much simpler surface to deal with. So obviously our x vector is x, y, z. Quite self-explanatory. But then it's like, what's our matrix A? How do we work this out? And the way I like to work these problems out is if we take some matrix, it'll be a 3 by 3, and we know that it's symmetric. So you can flip terms across the diagonal and they'll be the same. So I like to label the matrix like this. I just find this makes it a lot easier. So if we have the x squared term, it's where the x column and the x row line up. And it'll be whatever value we have there. So it'll be 5. So this will be 5. Then y squared is when the y column meets the y row. So then we just put 3 in here. Whoops. And then same thing here. Z squared, it's when the z column meets the z row. And we just have a 4 there. Okay. Now we've done these terms. Now xz, we look at when the x column meets the z row and when the z column meets the x row. So we could have this position here. So this is x and z. This is also x and z. Since we have two positions, we just split it evenly across it. So we put 2 here, 2 here. Because when we end up multiplying it out, the terms will add together and it will give us 4. So we have 2, and we have 2. And this checks out because we're just flipping this across the diagonal. So it's symmetric so far. And then the same thing goes for YZ. It'll be here and here. And since it's 4, we split it evenly across the 2. So we get 2 here, 2 here. Oh, whoops. 2 here, 2 here. And since we have no x, y term, this will just be 0. So we can confirm that we have got a symmetric matrix. If you flip everything across the diagonal, it's the same. So that is indeed what our matrix A is. So that's just a way, writing the x, y, z, it just helps me visualize what this thing's supposed to look like. So we've got our x, we've got our A. Okay, now we want to express it. We've got this, but recall that the next step is that we have to diagonalize A. So we want to calculate the eigenvalues and the eigenvectors. So I'm not going to sit here and go through the very tedious process of doing the characteristic polynomial and all that stuff. We'll just take for granted that these are the eigenvalues, these are the eigenvectors. Trust me, like these are the numbers, these are the right numbers. So what we can do is we've got our eigenvector matrix and our eigenvalue matrix. We just construct that from this. Now the catch was that it has to be orthogonal. Has to be an orthogonal matrix. We can't just put any matrix in there that has eigenvectors and be like, allow it, because that won't work. That won't work. So an orthogonal matrix is one such that the column vectors in the matrix are orthonormal, or they're all orthonormal, which means that they're at right angles to each other, and they're also of unit length. So yeah, so they're mutually orthogonal, and they also have a magnitude of 1. So if we look at our eigenvector matrix here, just by observation, like 1 squared plus 2 squared plus 2 squared, that gives us 9. So the magnitude's 3. So this immediately not orthogonal, because these vectors here are not orthonormal to each other. They're orthogonal, but they have a length of 3. So we rectify that by just, so we just scale it, and we rectify that by just dividing everything by 3. So this here is, we have a set of mutually orthogonal vectors, and they all have unit length. So this is like the vectors in there are orthonormal, which means that Q is an orthogonal matrix. So now we can diagonalize it, because we had our matrix D. We've got this here, which is very nice. So then it's just a matter of mashing it all together. So it's quite nice if we have an orthogonal matrix and we take the inverse, it's just the transpose of it. So it saves us having to think about inverse matrices, which is not fun. No one loves to think about that. So we want to remember this here. So I'll just get to, so we can actually write this, this expression. We can rewrite our matrix diagonalization as this long expression here. And we also want to recall that x, our new set of axes, is Q transpose x. So that means that it'll be x, x transpose Q transpose. Yes. So what we can do is we can substitute this new, our new set of axes that we're forming, we can substitute this into our matrix diagonalization. And this here is simply just our capital X. And this here is also our capital X. So now, making this substitution, our new set of axes, capital X, capital Y, capital Z, we can now write our thing in the form, in this form. And this, you'll come to see, is so much nicer because we have X, Y, Z, and then we just got our eigenvalue matrix. Let me grab that, 1, 4, 7. So it's just 1, 4, 7, 0, 0, 0. And then when we expand this out, we no longer have to worry about all these weird rotated terms. We end up with a really nice surface like this, just by expanding it out. So we get this nice surface, which is so much easier to visualize, so much easier to work with. Now, it'll look a bit like this. We get an ellipsoid. Now, it's all nice in large x coordinates, but we need to bring everything back to small x. And we know that if we know that taking q transpose of x gives us big X, we can just multiply it by the inverse here, which will give us a way to go back. So we get this like bijective mapping between large X and small x. And that's just by multiplying this matrix Q. So in other words, we take every point in this X, big Y, big Z, and we multiply it by Q and get this mapping that takes it back to our original quadric surface. So yeah, that means that if we have this point, 1, 0, 0, it gets mapped to Q, 1, 0, 0, because it's just, this is our map that goes from small x to large x and vice versa. So now we want to find the principal axes, the type of surface, okay, we know what type of surface it is, and the points that are farthest and closest to the origin. So our principal axes here are just the column entries of Q, of our orthogonal matrix. That denotes our principal axes. So that's sweet, we can just rip that straight from the matrix. And now the closest point to the origin in the x, y, z plane is this. And the way we can sort of work this out is we take our original function. Let me go back to it. It's quite far back. Yeah, so we take this, and if x is 0, y is 0, and z is not, then we just end up with an equation like 7z squared equals 1 on square root 7. And this will be closest to the origin. So that's where we get that point from. So I know I'm going through this quite quickly, just kind of strapped for time. So we found the closest point in our large x, large y, large z, and now it's just a matter of plugging it into this bijective map that takes it back to small x. And that map is just the matrix Q. So we multiply this by the matrix Q, and I'll save you again the matrix multiplication, but it's just, if you really want to do it yourself, you just mash these into a matrix and then multiply it by this vector. And the corresponding points that you're going to get is this. So this will be the closest point to the origin on the original quadric surface, like the yucky one that we don't want to work with. And if you're curious, this is what the quadrics that we're working with look like. So this red one is the initial one that we started with, and it's this disgusting rotated thing, like it just looks bad. But then when we go into the big x, y, z coordinates, we can map it and rotate it to something that's fixed and it's nice to look at, right? It's a simple ellipsoid shape. And that's the really nice thing about these quadric surfaces. So yeah, that wraps up matrices, for that stuff. Or the quadric surface stuff. So we move into systems of differential equations, and matrix methods, very nice. So let me get to the, yeah, here we go. So if we have some matrix that we can represent a system of differential equations with, and the easy way to rip the matrix out of this is you just take the x value here, it's there, y value here is the same as there, this here is this, and this 1 is that. So this here, when we expand it out, gives us the system of differential equations. Of course, when y is y1, y2, and this is going to be y1 dash y2 dash. So when we convert this into matrix form, this is our system of differential equations. We write it very concisely like this. Now, the general solution to this equation, or the system of differential equations, says that if we have linearly independent eigenvectors, v1, v2, etc., with eigenvalues, lambda 1, lambda 2, etc., then our general solution is this. It's this sum here. It's some constant multiplied by our first eigenvector, e to the eigenvalue times t. This is our general solution. So we find eigenvectors, we find eigenvalues. So we take our matrix that we started with, which was this. This represents our system of differential equations. And then what we do is we find what the eigenvalues are. So it's as simple as finding the determinant of A minus lambda I. So this is the same, this is just comes straight from the eigenvector equation. So we get this, this system here. We end up with like a polynomial, a quadratic in lambda, which we can factorize very nicely into this. And what that tells us is that our eigenvalues are -7 and 5. So what we do is we sub that into our eigenvector equation. So we say that what this implies is that, whoops, this thing doesn't like me. Oh my goodness. We say that V is -7V, and that AV is 5V from our eigenvalues. And then it's just a matter of moving it over to the other side. So we get this. And then moving this over to the other side, and we get this. And then simplify the matrices, row reduce them, then we get these eigenvectors. So this, we can just sub into our equation. We can just sub it into that sum that we had earlier. I don't know why this thing keeps moving over. So yeah, we have this nice set of eigenvectors and their corresponding eigenvalues. So to wrap it up, we take this sum here, where ck is some constant, and then we plug first eigenvector in, first eigenvalue in, second eigenvector in, then second eigenvalue in. And we end up with this expression. And if we just do the matrix multiplication here, multiply this and this by these terms, and doing it the same with the second bit here, we end up getting this this corresponding vector, which tells us that y1 is c1 e to the -7t, c2 e to the 5t, and that y2 is -c1 . So what we've got is our system of solutions just in a vector form, and that corresponds to the solution to y1 and the solution to y2. And then obviously those constants, if it were an initial value problem and they said that y1 of 0 equals this and y2 of 0 equals this, then we would solve for c1 and c2 simultaneously. But otherwise we just leave it as is, and we get all the solutions to the original system of differential equations we started with. So yeah, that wraps up all of matrices. So quite a lot of content, moving very quickly. But I'll pass it on to Rosh. Yeah, sorry, I went. Sorry.
You did so well. I'm sorry, can everybody hear me? Wait, can you guys hear me? Test. Okay, guys. Give me a moment. So, hello everybody. I am from Bluesat. So Bluesat is a UNSW student. Oh wait, sorry. Hi, I'm Rosh, and I'm from Bluesat. So Bluesat is a UNSW student space engineering project society, and currently we are undertaking 3 major projects: high altitude balloon, off-world robotics, and our satellite communication ground station. However, we have also done a range of CubeSat projects in the past. If you would like to find out more about this, our Instagram is UNSW_Bluesat. Like there, you'll find a link tree and you'll find our website and your application form for Try 2, I think. Not yeah, if you have any questions about what we do as a society, as a project society, feel free to reach out. Without taking more of your time, I'm going to start with ODEs. Yay! Okay. first of all, what is an ordinary differential equation? So a differential equation is an equation that relates to an unknown function with its derivatives. And the reason it's called ordinary because, well, we derive it ordinarily, not partially, which is, a cliffhanger to the next topic. So before we go on, we're gonna do some terminologies. So the order of an ODE is the order of a highest derivative. And an ODE is said to be linear if the unknown function and all its derivatives appear linearly. So what does that mean? See, if I read that, I wouldn't be able to understand that. So let's go through some solutions. Go through some stuff. So looking at this, we can tell that this is a second order ODE because d squared y and dt squared. And I can tell that this is linear because dy is just by itself. But for question 2, this would be a first order. But this is not linear, but this function is not linear because dy is like y squared. So how about question 3? What do you guys think? What is the highest order? What's the order of this function? 3, right? Because, well, this is the highest order, so it's third order. But is this function linear? Okay, why is it linear?
Y is by itself.
Yes, good job. So it is linear. Okay, how about question 4? What's the order of this differential equation? Second? Good, because this is d2y, d squared, so this is second order. How about its linearity? Is this function linear? Yes. It's actually not linear because it's a cos y. So because this is a function of y and this is cos y, so it's not linear. But it's okay, rather make mistakes now than in the exam, right? Okay, let's try one more, the last one. Question 5. So what's the order of this differential equation? 2, good job. And how about is this function linear? Yes, okay. So we're gonna start by solving some ODEs. So there's 2 examples here. The first example actually has already been done by MathSoc 2 years ago. So if you watch the 2018 revision seminar, they went over this. Because we're short of time, I'm just going to go straight to the newer problems. So so this is taken from 2021 term 3 question 3. So if you want to do it with your Mobius class open, feel free. So your classmate Ruth wants to solve the following ordinary differential equation using the substitution v equals y over x. That's the differential equation. A, help Ruth by rewriting the above equation in terms v and x. So let's do part A first. Okay, so there's a few ways to solve this, but I do it specifically like this. So so in part A, they want you to find dv over dx. So we know that v is yx minus 1, right? So therefore, dv over dx is just u is y, then du equals dy over dx, then v is x minus 1, then dv is minus x minus 2. So we get dy over dx, 1 over x, minus y over x squared. So with this, what I would do is I would sub the dy dx into it. So dv over dx equals to, we'll get x squared plus 3xy plus y squared over 2x squared times 1 over x minus y over x squared. So after this, I would use the substitution y equals to uv. And then, I'm sorry my handwriting's kind of bad. I'm not really used to this board. So we get x squared plus 3x uv plus, no, I'm sorry. I'm so sorry, guys. It's vx. Whoops. So vx squared over 2x squared, 1 over x, and then we have minus vx over x squared. So obviously the x squares in here, they cancel out. So xx and then eventually we got 1 plus 3v plus v squared over 2x minus v over x, which gives us 1 plus v squared over 2x. So there we go. Okay, so now part B. So using part A, help Ruth solve the ODE to find yx. Well, let's rewrite that. So So dv over dx equals to 1 plus v squared over 2x. So this is a separable ODE, so that means we can just multiply it across, and eventually it will be 1 over 1 plus v squared dv equals to 1 over 2x dx. So with that, we can integrate both sides. So the right-hand side seems a lot more easier to solve. So we're going to solve that side first. So this is a common integral. So we get 1 over 2 ln x plus c. So we know the right-hand side. Now, the real challenge is trying to integrate the left-hand side. Okay, so it's going to look scary at first, but what we're trying to do is we need to try to rearrange the denominator into something that is similar to the format of a formula sheet. So based on like intuition, we're gonna try to complete the square with this. So I'm just gonna casually complete the square at the side. Yeah, okay, so there's that. So eventually, when we write it, it'll become v plus half squared minus 3 over 4. So another way we can rewrite this is 1 over v plus half squared minus root 3 over 2 squared. So it's starting to look more similar to, sorry, I think this is plus. So it is starting to look more similar to what we know. So let's like simplify this even more, and let's use substitution. So let's use the substitution u equals to v plus half. So and then du is just du over dx is just, sorry. And then, you know, when we derive it, it also like becomes 1. So when we do it, it's 1 over u squared plus root 3 over 2 squared du. I'll just put that here. So this is actually a common integral, so it is the one with inverse tan. So this comes from, I think, if I'm just gonna whip out. Okay, it's 1 over, sorry. So if it's 1 over a squared plus u squared du equals to 1 over a tan minus 1 u over a plus c. So that way we are going to get that way we're going to get 2 over root 3 tan inverse minus 1. Oh, sorry, tan inverse u over root 3 over 2. And then if we do, and if we expand it back with u to that, we will get 2 over 3 tan minus 1, 2x plus 1 over root 3. Yeah, there's a slight typo over here because, yeah, there we go. Okay, and this slide will be posted into the MathSoc website. So I'm just gonna, like, we're gonna, can just do it in your own time. Okay, so far we have only solved for separable ODEs. But what's gonna happen if the ODE is not separable? So there's a very fun little thing called integrating factors, where basically if the first linear ODE is in this form, what you can do is you can take the integrating factor, which is just e to the integral of whatever's in front of the y value, or you know, whatever this could be, and then you multiply it through. And then once you multiply it through, it goes into this form, and then that way when you integrate it, it's actually a lot simpler. So we're just going to do a question. So this is from 2023 term. I'm sorry. Yes. Oh, okay. Okay, I'm going to prove to you that while doing the question. Okay, so I'm just going to rewrite this. Guys, I'm so sorry if my handwriting's really bad. I feel like my handwriting's really bad. dq over dt plus 12q equals to 2 plus sine 2t. Okay, so firstly we want to find the integrating factor, right? So the integrating, so since, you know, like looking into like this format, it's we know that this is px. So what we can do is that guys, I'm so sorry, there's another typo. It's actually supposed to be half p. I'm so sorry. Anyway, so I'm just going to rewrite that. Sorry, it's q. Gosh. Ugh. Okay. So 1 over 2 dt. So therefore, we get the integrating factor 1 over 2 t. So after that, we're going to multiply through the whole equation. So it's going to be e half t dq over dt plus half e half t dq over dt equals to 2e half t 2 plus sine 2t. You understand until, is this part okay? Sorry, thank you. Gosh, thank you. Good job. Yeah, is this like, do you understand until this part? Understand this part? Okay. So let's look at this. Okay. Okay. So we know that the product rule is v du plus u dv, right? Okay. Isn't that similar to that? So let's say if I want to take the d dt of e half t q. So let's make u as e half t, du is half e half t, then v is q, it's going to be so that's where we got this from. So that once you get the integrating factor, once you multiply it through, it will just become like that. And we just proved it. Yay! So since what we're going to do is going to take that, and we're going to rewrite that as the differential form. And now we're going to integrate both sides. So it's going to become, because we are integrating, the d over dt disappears, and now we are going to integrate this. I'm sorry if you're watching online, I'm just like drastically going down. I'm really sorry. So in the question, you're given a form that's like, so in the question, you're given like EAX, like sine omega t is equals to like like, because I think this is a standard integral as well, over a squared plus omega squared, and then you have minus omega, sorry, just gonna push that aside. I think it's like omega cos omega t plus omega sine omega t. Like you're given that in the question, like it's like a standard integral. Yes?
Alpha sine.
Alpha. Oh, sorry. Thank you. Right? Is this correct?
Integral is left-hand side.
Okay. So we will eventually get we will get that. And the question states that where the pond is initially free of chemical, so when t is 0, q is also 0. So we're gonna substitute that into it to find c. So when t is 0, this is going to be 1, but this is going to cancel out, so that's 0. It's going to be 1. This is going to be 1. Cos 0 is 1, and then sine 0 is 0. And then eventually we will get c is minus 120 over 17. And then we can substitute that back into the equation. So like E12tq equals to 8e half t plus 8 over 17 . And since we can simplify it, we can do q equals to 8e half t plus 8 over 8 plus 8 over 17 minus 2 cos 2t . And then we have left hand side and right hand side. So this one we just solved for the left hand side. So now all we need to do is just add from, oh, sorry. I lost myself there. Sorry, no, yes. And then, so that is the final answer. So, yes. Yeah. So now we're going to move on to second order differential equations. So this is called a homogeneous equation. So basically when it equals to 0, when like d squared what? It's like this is another way to write it. And then eventually this would produce a characteristic equation of that. And we would get values for lambda 1 and lambda 2. So what this would do is that this is really helpful for finding your YH, which is the homogeneous solution part for your second order differential equation. So there's 3 cases to when, I know this seems a bit like, oh my god, what's happening, but I'm just going to tell about I'm just gonna like give like the notes first, and then we can go over the problems. So if both of your lambdas are real distinct roots, your homogeneous solution would be AE to the power of whatever your lambda is. But however, the second case is that if you have equal real roots, it would be e to the power of your, like e to the power of your root x, a plus bx. But then if it's a complex, but then if your lambda is complex, we would get a cos and a sine. And then, so there's another way to solve your second order differential equations. So not all second order differential equations will equal to 0. Eventually they will have, eventually you'll come across problems where it equals to a function. And for that, we need to find y particular, so the particular solution. So when you have a second order differential equation like this, the way to solve for y is need to find the homogeneous solution and need to find the particular solution. So the homogeneous solution comes from the left-hand side, which is where you would see like where you would find the differentials, and then the right-hand side is often like again like a function. So the right-hand side is where you'll find the particular solution, and the left-hand side is often where you would find the homogeneous solution. So there's a few ways to find the particular solution, but like a way would be, but not just a way, but like a way would be the Wronskian method. So the way it does is that it takes what you got for your homogeneous, so whatever you got from here. So let's say your YH is AE x and BE to x. What it does is that and then to find the AE would be considered as y1 x, and then this one would be considered as y2 x. Same thing for this, but except if it's equal real roots, it'll just be same for both. And then, but for this one, but for complex conjugate roots, you just use the cos and the sines. So so if you get AEX and AE to the power x and BE to the power 2x, your Wronskian would be EX, E2x, and then the differential of e to the x is e to the x, and you just get 2e to x, and then you find the determinant of that, which will give you something, which actually should give you 0. Yeah. Anyway, so it's time to solve some problems because that's how we're going to learn. So from term 1, 2021, it's an exam paper. So use the method of variation of parameters to solve the second order differential equation. So the way to solve a second order differential equation would always be, again, YH plus YP. So Y homogeneous and Y particular. So since it's a lot easier to find the homogeneous solution, let's find that first. So y dash dash plus 9y, they would produce a characteristic equation of lambda squared plus 9 equals to 0. Does everybody understand how I got from here to here? Okay? Okay, so from this, we would get that our lambda is plus minus 3i. Okay? So since it is a complex conjugate root, our homogeneous solution would be in this form. So, YH, Y homogeneous is E, well, since there's none, so it's 0x, A cos 3x plus B sine, sorry, it's T, gosh, 3T, which is just A cos 3T plus B sine 3T. Okay? So where this is y1x and this is y2x. So now we are going to find the Wronskian, where it's just cos 3t sine 3t will give you minus 3 sine 3t and 3 cos 3t. Give you ADs, or 3 cos squared 3t. Then this is minus minus plus 3 sine squared 3t. So it just cancels out nicely because cos squared sine squared is 1. Almost at 0 there, but it's fine. Okay, so now we find our Wronskian. Amazing. What does that mean? We can plot it into this formula to find our particular solution. So I'm going to section it out in parts. So I'll solve this first, and then I'll solve this part. So also oftentimes they would call this as like U1, and they call this like U2. So I'm going to be using like that notation. Okay, so U1 equals to, well, sine 3t 3 secant, sorry, 9. Because we're plotting in fx, and fx is this. Fx is the right-hand side of the equation. Then over the Wronskian. So 1, 3. And then we know secant is, am I pronouncing it correctly? Is it not secant? Second? Secant? Okay, sec. Okay, so we will get 3 sine, so since the sec 3t means it's 1 over cos 3t, so it's just cos 3t. And then if we differentiate cos 3t, we will get 3.
The sine wasn't divided.
Sorry?
Can't cancel with the sine. The sine's got a 1 in front of it, and there's a 1 next to it. Wait, is it multiplied together or
Yeah, they're multiplied. This is dot, like, sorry. Yes, multiply. Oh. Okay. Anyway, so since cos 3t, since when we differentiate cos 3t, we would get 3 sine 3t. So it's a standard integral. So your answer would just be ln cos 3t. So now let's find u2. So integral of cos 3t times 9 secant 3t over 3. Again 3. And then this one is nice because it cancels out nicely. it'll just be 3t plus c. Honestly, we can, yes?
The first integer should be -3 ln cos. Oh, I think it's just negative. Oh yeah, sorry. It's negative.
Wait, it will, yeah, so,
Yeah, because the derivative of cos you get negative sine. So it'd be negative ln. And the 3, yeah,
is it?
it's a negative ln.
Sorry guys. I'm sorry. Wait. No. I'm sorry. Trust me, I can do math. I'm just really nervous right now, like presenting in front of everyone. Anyway, so going back into that, so our homogeneous solution is a cos 3t plus b sine 3t, and then since y particular is this, so we're going to add in, since it's y1, so it's going to be plus cos 3t, so minus we'll get a plus, ln minus sine and that is the solution to solve the second order differential equation. Yay. Yeah, is there any other questions? Everything's okay? I'm sorry about that careless error over there. Yeah, I'm really sorry about that. So, actually that is pretty much it for second order differential equations. So I know like in the course there's stuff like force, oscillation, resonance, but everything is just like a different mixture of y equals to yh plus yp. But however, there is like, honestly, looking at the wrong skin, you might think like, oh, that's very time consuming. Surely there is like an easier way to do it. There is, but there's also like faults to it. So since we're running short on time, I'm just gonna really quickly run through it. So force, oscillation, resonance. So when dealing with a system of subject simple force oscillation, we often need to solve equations in the form of this. So there is like a general intuition, like a general guess for the particular solution of y. So let's say if the right side of the equation is like 2e like 5x. That means we're gonna generalize it to ax, 5x, and then eventually we're just gonna like differentiate it and differentiate it again, and then we're gonna sub it back in. We're gonna sub it back into the differential equation and then make it equals to the function to solve for our undetermined constant. So I am going to run through an example for when, so for example, like let's take this question. I'm going to run through it really quickly. I'm so sorry. A force vibrating system is represented by that, and describe the y displacement system over time c equals to 0, 1, and 2. So this is a really good example of when we can see when to use method of undetermined coefficients and when to use the wrong skin. So you might think like, oh, I already have this. Why do I need to use the wrong skin? Well, after this, I'm going to show you where it kind of like breaks down and you kind of just have to use the wrong skin. And also, we can use the method of undetermined coefficients only for when all the coefficients are a constant number. So we could use the wrong skin. We could use the wrong skin to like just straight up just solve with like 2c, and then plotting 0, 1, 2 like later. Or else we can use the methods of undefined coefficients. Anyway, so I'm just going to go over for when c is 1. So when c is 1, we would get y equals, and then we would get the characteristic equation. Okay, we all understand how I went from here to here. And then that way we will get y plus 1, lambda plus 1, lambda plus 1, so therefore lambda is just minus 1. So therefore our YH is our homogeneous solution is just right? So now we're going to move on to the particular solution. So since it's 2 sine t, we can kind of have a guess that it will come in a form of that. So we can say that the particular solution would come in the form of a cos t plus b sine t. So that way, so we're going to differentiate it once. Also, like one way we can say it's also like the negative of that. So after getting this, we're going to sub it back into the equation. We're going to sub it back into here. So minus 2, that's plus. Going to equate it to the function, and that way when we expand it, it's going to be this and this cancel out, this and this cancel out, so that way we only get this. So we get minus 2a sine t plus 2b cos t equals to 2 sine t. So as we can tell, there's no value for cos. So we can just assume 2b equals 0, therefore b equals to 0. So that way we know minus 2a equals to 2. So therefore a is minus 1. So we know yp, so subbing it back into here, minus 1, so that's just minus cos t plus, well, 0. So now we solve for our particular solution, and we also have our homogeneous solution. So one way to solve it is, sorry, so that's one way we could do it by using the methods of undetermined coefficients. For the second slide, for when c is 2, it has 2 roots. It also has 2 equal roots, and we can do the same thing as well. However, at the case where c is 0, we get that lambda is a complex conjugate pair. And so because it's a complex conjugate pair, we get the homogeneous solution is a cos t and b b sine t. So this is a problem because if we were to transform this using the methods of undetermined coefficients, we would get the same function. So one way to mitigate that would be that we should just guess like t times whatever our undetermined coefficient is, and then we use the same process of differentiating. Gosh, we differentiate p, and then we sub that back in to figure out for a and b. And yeah, eventually, and I think that is it for second order differential equations. Just gonna give it a moment to load. Yeah, actually, any questions from anyone about second order differential equations? Yes, so I'm gonna pass the mic to Otto to talk about partial differential equations.
All right, give it up for Rosh. Thank you. All right, so where's my pen?
I took it with me.
Yeah, there it is. Okay, so partial differential equations. Essentially, you can consider it to be slightly more of the same, but there's like a slight caveat. We use this for specifically problems dealing with like heat equation, wave equation, physics, models, stuff like that, okay? And we're just gonna really dive straight into it because I do notice that we're going slightly over time, so we're gonna make sure we try and save as much of your time as possible as we lead into exams. So first up, heat equation. So over here, we have a variation with respect to time is equal to a scalar multiple of your second rate of change with respect to your position, okay? So we're treating our equation, U being your heat at a certain time and a certain place, okay? And we're really just talking about one dimension right now because that is within the scope of this course. So let's hammer at it. So with these equations, we get a number of assumptions that we take. This one, we won't always take it, okay? this one's just certain conditions where, okay, let's say the ends of the bar are a constant 0 degrees Celsius. What we can do here is apply this to our initial conditions, solve for some of our coefficients, and bam, bing, boom, we get our equation done. All right, so in other cases, we'll take some manner of function as like an initial setting of our bar and its temperatures, okay? This will come up in one of our big examples slightly later, but we'll see it. We'll just go on with it. Another important assumption that we need to acknowledge is what it means for a bar to be insulated, especially in the mathematical kind of sense. What it tells us is that the rate of change with respect to your placement, your space, the rate of change of your heat with respect to your position is going to be equal to 0 at the endpoints of that bar. So we're kind of saying, okay, here's our bar, it has 2 endpoints, and there's no real heat transfer occurring between the position immediately next to those endpoints, right? So we can't have an escape of heat from this system. Yeah, that's what insulation means. All right, so let's talk about the separation of variables in these kinds of scenarios. So, given a partial differential equation with variables x and t, we can make a number of assumptions, okay? The first assumption is very relevant for the course, okay? We're talking about separable functions, okay? We can separate it into the product of a function with respect to x and a function with respect to time. So, we go on, our general method for producing the equations and solving these equations will be as follows. There are 4 steps. The first one is to assume, like I said, that you have a function in terms of position and another in terms of time that you can separate it into, okay? Next thing is to substitute the product of these functions into their own respective differential equations, right? So we'll go over this in our next example, but it's just something to keep our minds and eyes out for. So, final 2 steps, we just solve the ordinary differential equations provided, and then we combine the solutions to these such that they satisfy the initial conditions. That's a bit more of the setting up, solving coefficients to give us a proper solution rather than a general solution. All right, now, little thing, we love the word superposition. If anyone has ever done ELEC Quad 1, you're going to have a little flashback. But essentially, superposition, it's the summation of linear components, okay? Rather, it's the linear summation of components. And we're allowed to do this in our solutions because everything's obeying by the same kinds of laws, right? There's nothing that's disobeying this kind of linear factor. Anyways, so 2 more extra little things. This one's scary, okay? Fourier series. Fourier series can be a pain in the butt, but if we know what we're doing, we can tackle it with the same manner of force. So, let's dive straight into our first manner of question. This one's from 2013. It's a bit of an old question, but it's still relevant, just for the fact that we're dealing with an insulated bar and we have a certain equation provided. So, let's go ahead with it. First off, how are we going to show that g dash over 4g equals f double dash over f, which is equal to some constant lambda? Well, what we can do is immediately just use this equation given to arrive at g dash and f double dash, okay? And from there, we'll be able to intuit things out. We want g dash on 4g, we'll just chuck it on the other side. We want f dash on f, we'll just chuck it on the other side. Too easy. Okay, now, what does this mean? Why is there a sneaky lambda here? Well, if we look at the left and right hand sides of our equation, we have a function with respect to space, with respect to position, and a function with respect to time. Well, the only way that these 2 things, as functions, can be equivalent is when we're dealing with a constant, okay? And using that kind of intuition, we arrive at the exact same thing I just said. Okay, so moving on to the next question. By the way, if you have any questions, please raise your hands. I'm just trying to hammer it through. Okay, so question 2. We're going to try and show that the possible solutions are of this form. How do we do that? Well, given the assumption that lambda equals a negative square, we can go ahead and look at our equation with respect to position. And you'll see that this is like awfully reminiscent of something called simple harmonic motion that you would have done in high school if you went here. But anyways, so we'll dive into it. And because it is reminiscent of simple harmonic motion, that is, I have a point, I go up, I go down, and it moves like a sine wave, some manner of sinusoidal action. So that implies that we have a sinusoidal solution. All right, we're just diving in. Since we're assuming it has this manner of solution, we're going to then apply our boundary conditions. I kind of skipped over this in the setting up of the question, but the initial condition is up and up and up. There's a lot of slides. Okay, it is insulated, okay? Since it is insulated, we can intuit some extra information out of the partial derivatives. My bad. Okay, and here we are. So, considering the first partial derivative, we can demonstrate that since sine 0 is 0, we can kick this out. Since cos 0 is 1, we replace that with 1. And we have that k times some coefficient a is equal to 0. Well, we can't have k just equals 0 because k is meant to be our like regular thing that we can change and vary across all possible numbers that it seems relevant to. So we can't have k as 0. We must have that a is 0 by null factor law. Boom. Okay. Now, brings us to our other equation. Considering the opposite endpoint at pi, we have the sine component cancels out once. Sorry, we're talking about the derivative. So we're gonna deal with, oh, that got louder. We're dealing with substituting pi here and here, okay? And what we can tell from this is that minus kb sine k pi is going to equal to 0. And why is this? Because we just said that a is 0 before. That means we're going to cancel out this leftmost term in the pi expression. And something that we really want to look out for these types of questions is we don't want to make everything trivial. What that means is if I just say, oh yeah, what do you mean? fx equals 0, full stop. That's kind of boring and it's not completely correct. So we don't want b to be 0. That's the only thing holding us back from nothing, the void. So what do we say? We say that by null factor law, something else has to be 0. So we look at this sneaky sine k pi and we say that it must be 0. That implies certain values of k are what we're going to be looking at. And so we talk about k equals n for n from 0 to whatever number. Okay, we'll just consider positive ones for now because it's all really the same if we think about it too hard. So, given that we're talking about k equals n for some integers, we have that this entire sine component goes to 0. So fx equals b cos kx. And so for all possible solutions, our n solutions, they are of the form bn, some constant, coefficient, multiplied by the cosine of nx. Too easy. All right, let's keep on pumping forwards. So, third part of this question. We're going to try and find all possible solutions of our time function, right, g. We're given that g dash equals minus 4n squared g. Mind you, we've already substituted k as n, and we're kind of considering just the nth components of this kind of time function, right? And from here, since we're only considering the first derivative, we can apply a similar method as we saw earlier. It's our frickin' exponential assumption, right? Integrating factor, that's the word. Okay, So from there, we can just whip this thing into the exponent, and bam, it's done. Attach t, your derivative works. Too easy. All right. And so, quite intuitively, we've arrived at all solutions of GT. Fantastic. Now we have a slightly more difficult question. Okay, this is from 2013. We're dealing with something a little scarier. Okay, so from here, we're just going to consider our function given the interval. Okay, and from here, we're going to try and like massage this equation into our Fourier series, okay, for time is 0. So, how do we do this? We go ahead and we just match things up. We know that uxt is equal to the summation, the superposition of all our solutions. These solutions are of the form of the product of fn and gn, okay? And as we've calculated what those are, we can then express this product quite well. And we see that certain things match. So, moving forwards, we look at what happens when we apply Fourier for the time equals 0 kind of format. Our exponential disappears because we're just talking at t is 0, it becomes 1. So, we just have bn cos nx. How strange is that? We have bn cos 0 is just bn. So for n is 0, we just have a half. And then for the rest of them, we got this funky little thing attached to cos nx. Well, quite intuitively, we can go ahead and identify the coefficients and match them. Because in a kind of a vector space oriented method, we define Fourier series as the construction of space using an infinite number of independent vectors, which are given by all your different cosines with different frequencies. Well, sinusoid waves with different frequencies. Anyways, okay, so moving from there, as I stated, we have b0 equals a half, and we have bn equals this funky looking thing on the sum, okay? So that's 2 on n pi sine n pi on 2. Any questions so far? Fantastic. Okay, so that brings us to part 5. It's a bit of a lengthy questions, as these ones usually are. So, what happens as temperature goes to infinity? Now, a few things to note here. We called that this was an insulated system. Okay, that means all the energy pretty much remains inside the system. And we also know a funky thing about Fourier series and our sinusoidal functions. We'll get more on that in tomorrow's seminar. But what I want to say here is, if you go from time to infinity, your exponential starts doing something. And it says that all of these sinusoidal components that are, you know, n is not equal to 0, they go to 0. Too easy. Because for n not equal to 0, you have a decay. Because there's a decay, your magnitude of all these cosines goes to 0. And you're left with a funky little function, constant, left. And you can imagine quite intuitively, if you have a really hot bar, okay, if you have a like super hot bar at some points, okay, and it's like super hot there. That's like a nose and 2 eyes. Anyways, so from there, we can really just consider over time that heat is going to disperse, okay? And that's kind of logic we're going to use for a lot of this conservation type style thinking, okay? Just as intuition for these types of questions. All right, and so we see what I just said. Too easy. Okay. A little bit more of a comment. Unless specified, you might want to try like multiple types of constants lambda for your solutions, because we're not always necessarily going to be looking at, okay, what if lambda equals minus n, like minus k squared or something, right? We're not always going to get that. It might be 0. It might be, heck, it might be like greater than 0. How crazy is that? Okay, we'll see that a little bit later. But first, we're going to just look at a bit more theory. What is the wave equation? We love the wave equation. It's quite important in physics. And so, You should have seen this in like physics 1A, end of the term. It's a pass-fail course, no one really cares. Anyways, so let's go on with it. We have a number of boundary conditions. First being that instead of considering heat, we're talking about displacement now. Displacement of a string as time progresses, as we look at different places, right? So that gives us two variables that we're varying, that are in variation. And we have one dependent variable, our function, which is the displacement. Okay, fundamental things. We got this funky equation, which is just saying that your acceleration of time is equal to some scalar multiple of your, positive scalar multiple of your acceleration of like position, if you're talking about like derivatives in that sense. All right, so more initial conditions. We can say that, okay, this string is going to be bound at both ends so that those endpoints can't actually move. So they're always going to be stuck at 0. We're just kind of intuiting, okay, physically, what does this mean in math? Stuff like that. All right, now note, while we can have an initial condition for the displacement, we can also have an initial condition for our velocity, okay? And this becomes very important, especially when you're considering, okay, if I have a rope attached to the end of the room and I shake it, there's some manner of velocity traveling along that rope, which has to be accounted for in any calculations concerning it. All right, so let's get on with a standard solution, okay? We're going to look at D'Alembert's, I don't know how to say his name, but I think that's correct. Anyways, D'Alembert's solution provides us a manner of approximation almost, okay? We have this simple thing that's saying, okay, given certain single variable functions, we have a general solution to the 1D wave equation, okay? It doesn't tell us too much, but as we get more information, we can make better approximations and better calculations. And so we can express our displacement as the average of 2 points in time, okay, as time goes along, plus some integral of our velocity, okay, GS indicating our velocity as prior, stuff like that. Okay, so what are the major differences with this thing? It changes really just our method of solution, okay? And you'll see that slightly further along, but let's just dive into another question, okay? Any questions just remaining the content? Okay, fantastic. Let's move on. So first up, let us just consider we have let u double t equals nx nu double x. And what this tells us is that this number right here is equal to c squared. So c is going to be 3. We're taking it as an arbitrary positive number because it really doesn't matter. We have a positive side and a negative side. All right, so D'Alembert says there's some arbitrary functions. I think it's psi and phi or something, right? Something like that, satisfying the wave equation. Given certain initial conditions, they want us to prove that the wave equation is solved by just a summation of your velocity, okay? Summation of your, actually, no, it talks about g as initial displacement, sorry. Velocity is 0. So, we get cracking, and we're just going to say, we're talking about two new variables, which are just going to express x plus 3t and x minus 3t, okay? And so that's going to allow us to represent u, our displacement function, as the summation of some manner of functions phi and psi, okay? So, what can we do from here? We can apply chain rule, because all we know is there is an initial condition and there is an initial velocity. This one looks rather tempting because it's 0. So, applying chain rule, we differentiate and we get two components because we're talking about partial differentiation. As stated before, we follow all roots when considering like routes of differentiation when considering partial differentiation. Anyways, we move on and we conclude that since v and w are equal to x plus and then minus 3t, when differentiating with respect to t, we get a scalar in front and one of them becomes negative. Okay, that's just standard chain rule stuff. And then we have our initial condition. We have the initial condition that u of x at time 0 is given by the function g of x. From here, we can imply the other thing I said before, which is that the 0 is rather tempting, and determine that now we have two manners of equations for two functions. This seems a lot like simultaneous equations. And in fact, you're correct. You're correct because we can integrate this side to give us another thing in terms of these. Since the subtraction of two derivatives is 0, we have that the function's difference is also going to be a constant. So, provided that information, we can progress. We say that since they only differ by a constant, the function g of x actually is very closely tied to our other two functions, psi and phi. And so, we can interpret both as functions of g of x. So if phi is that, psi is that, well, I'll draw the other one. Oops. And so, just expressing the sum, we can see that those ones cancel out, and substituting for our values of x being x plus 3t, x minus 3t, we push forward, and we achieve what we wanted. Fantastic! Okay, any questions surrounding wave equations? Because I'm pretty sure the next thing is just going to be hammering out heat. Okay. Could you guys check the chat, by the way? Thank you very much. Okay, anyways. So, time for our big example. Okay? This is, once again, just considering heat, but we're going to consider all the possible cases. Okay? First up, let's just sort out that there exists some manner of constant k that gives us these equations for this partially differentiable equation. Partial differential equation. That's the word. Okay. So it's insulated, has the equation. That number is important for some of our scales, but we'll move forwards. So first up, AI. We're going to look at how do we get these? Well, once again, we just rearrange. We get g dash on 48g equals f double dash on f equals k, some constant, which is still a function of time and position. So, fantastic. Same work as before. We're just applying it again. And so, we prove that there is some manner of constant, k, that satisfies this, because then we can intuit two different equations given by k equals this one and k equals that one. Too easy. All right. Mind you, this is given that g and f are non-trivial solutions. Okay, just something to be mindful of because you don't want to be dividing by 0. Okay. So, next up, what's a double I? We're going to determine the boundary conditions. Well, before you might have noticed that I mentioned insulated. That's a pretty big hint. So, as we said before, since it is insulated, we have that the rate of change of our temperature with respect to position at the endpoints are going to be 0. So no heat can escape the system. It's a really nice way of thinking of it. Okay, because that is the definition of insulation. Too easy. Okay, now we're going to look at B. Explain why, when k is a positive number, we only have trivial solutions. Well, that's rather problematic. So, let's think about it like this. Consider f double dash minus k f equals 0. Okay? That was an equation given just beforehand. Now, what this tells us is that your acceleration of the system is a scalar multiple of your temperature at that point. Okay? So you can think of it relating to like single variable calculus, stuff like that. If you have a increase in your position, your acceleration of your rate of change of your rate of change of heat increases, right? And so that tells you that, okay, if for some manner of point after this in the future, right? Sorry, no. For a future position, right? If this has a height, then it is going to increase even more further on, and further on, and further on. However, there lies a distinct problem here. We're talking about f double dash. Okay, that tells us that the f dash increases for some k, so some like f beginning higher than 0. Okay? And the same thing goes if it begins less than 0. Okay? It pushes further down and further down and further down. But we just had a boundary condition stating that your derivative at the endpoints is 0. So while we might be 0 over here at one endpoint, you're not going to be 0 up here or down there. Because quite intuitively, you're super far away, you're going to have a high acceleration that's, it's going to monotonically increase or decrease. And so you're just never going to reach that manner of point. And so the only way you can do this by some sense of contradiction is by starting at 0 and ending at 0, which is, quite frankly, the definition of a trivial solution. It's just 0. Okay, so here's some words I wrote. I just spoke it pretty much. Anyways, further on, you can read that stuff in your own time if it helps you so. And so, let's look at question C. What occurs when k is equal to 0? Okay, so if k is equal to 0, and we're still imagining these same boundary arguments, we're still considering these two equations, we have to be careful of one thing in particular. If k is 0, then that implies that g dash and f double dash are 0, because we're talking about a numerator. And we have to be very careful about dividing by 0 in these instances. So we can't exactly just immediately jump and put up our hand and say, okay, obviously f is 0, g is 0, trivial solution. We can't do that, right? Because we have to be careful about dividing by 0. But it does tell us another piece of useful information. If k is 0, then f double dash, that's not how I draw that, whoops. F double dash equals 0. So it's not going to be accelerating anywhere. And we know that f dash equals 0. So that means across the entire line, there is no manner of up or down motion of our velocity, and the velocity remains at 0. If your velocity or your rate of change remains at 0, you just have a constant. And so we have some manner of constant. Right? Too easy. So that's what happens when you have k is 0. You often get like a constant system. There is no manner of like variation or dampening or spread or things like that. Next up, we're going to look at k equals negative omega squared. Okay, something less than 0. Now there are two parts of this question. The first part is, okay, as stated before, we know there are going to be an infinite number of non-trivial solutions, and so what would omega n be equal to for our nth solution, and what does the solution in terms of position represent? Okay, what does it look like? Followed by, once again, solving for time, which, just a hint, that looks like another of the same. So let's get moving. First up, k is equal to negative omega squared. We jump it over to the other side, and once again, simple harmonic motion, sine, cosine. Too easy. Exact same argument as before, okay? We want a is 0, so we chuck out that sign. We hate sine. We love cosine. It's very sec. Now, anyways, so considering the second argument, once again, a is 0, so we're considering what b omega sine omega pi is going to be. You're going to have omega is just going to be equal to n for some integers n, because we don't want b to be 0 and produce trivial solutions. Once again, same arguments. So we have omega n is equal to n, part 1. We have fn is equal to bn cos omega n x. That's our second part. And our third part we're going to do right now. And it's done. Woo! Okay, so just to reiterate, we're just using our, I always forget what it's called, but it's just intuition of an exponential hypothesis, okay? You're assuming that, okay, I differentiate something, I get it multiplied by something, chuck it in E. Too easy. Okay, so we have 2 more components to deal with, okay? First things first, we want to interpret it as a sum of these functions, okay? And then next up, we're going to be applying an initial condition to it, okay? To determine what these manners of coefficients are. Because before we're dealing with an, we're dealing with bn over here. It's rather messy with the number of coefficients we have. And so, first things first, let's consider how do we get UNXT? Well, we want something exact, okay? We don't want any of these funkier coefficients in there. We'll pawn them off to like Cn, okay? So we'll just say, okay, Cn, you're going to be equal to An, Bn. Too easy. So, from here, we just strip apart G and F to get cos nx e to the minus 48 n squared t. Mind you, we're writing it in this way just because this is coming directly from Mobius quiz, so you're going to want to touch up on that kind of syntax, yeah? Just because if you're going to lose marks in Mobius, heck, you're going to want to be wrong rather than just draw it incorrectly. So, part F, scary. We said before, we want to find Cn, and this initial condition doesn't look particularly nice. If we look at our initial condition, we only have terms of cos nx. Now, since we're dealing with a, Fourier series and we only have cosines, what we're going to want to do is, given that your initial condition is going to look something like this, okay? For like 0 to pi, it's 0 until like pi on 2, that kind of jazz, yeah? I can't make this just with cosines. It's too hard. Unless, now here's the trick. When we jump forwards next seminar tomorrow, we're going to discuss what I mean by a half period extension, right? And what that tells me is that, okay, imagine that it is even, and so that I can make it out of cosines. Because Fourier series is telling me that, okay, if even function, then you have a constant plus even functions, yeah? Because we can't make it with sines, they're odd, okay? And so that gets messy. So we make it an even function. So we're dealing with something that looks like that. And so we're going to integrate it. First things first, C0, our constant offset, we can just determine that the same way with this one. Too easy, okay? Integral of 1 on pi from pi on 2 to pi e to the pi on 2 minus x as described in the equation, yeah? But then determining Cn becomes a little bit of a hassle. So first things first, we're going to consider 2 over the period of f of x cos nx dx, right? Fair enough. Now, we know it's even, so we can split this in half, okay, and double our value, okay? So we get a 4 on 2 pi, which just becomes 2 on pi. We know that f of x, well, this part over here is just 0, okay? From 0 to pi on 2, it's just 0. So we can exclude that from our integral by like partitioning it. And we're only going to look at this little portion here from pi on 2 to pi. And that is going to be of e to the minus x cos nx. Now, as discussed before, you have like, usually in Mobius quizzes, they give you a little bit of extra info when they don't want you to like, oh, sorry, I did integration by parts 3 times and got it wrong. I don't know where I did it. That becomes awfully tedious. So they often give you like a little shortening of that. So I'm going to use that quite as I should, as you should. Okay. Okay. So we get something long and horrific because we're integrating e to the minus x cos nx. Okay. And from this sheet, it says that it's equal to e to the thingy squared plus thingy squared minus thingy plus n thingy. Okay. A lot of thingies, but as long as you match along your coefficients, like I'm saying alpha is -1, I'm letting beta equal to n, and yeah, it just works, okay? So now I have my boundaries to substitute in, and I get a mess. But the most important thing is that Mobius is green, okay? That's the fantastic part. Mobius is fantastic in getting you to write a mess and then rewarding you for it most of the time. All right, so that is going to give you Cn. And my final question for you guys. What is the steady state temperature of the bar? It looks a little bit similar, but remember, it's insulated. We have a decay. It exists. We just excluded it for the Fourier transform because that's when time is 0. And so time goes to infinity. We have an exponential that is, you know, negative exponent for n is not equal to 0. So we have e to the negative infinity. That goes to 0. And so we only take for n is 0. And that is your constant offset, okay? Because it says that everything has been balanced out. And so, another mess. Just as a little simplification of what I had written earlier. All right, and that is the end of partial differential equations. Thank you all for coming. And I know that we've run like, a horrific 50 minutes over time, but it's week 11, you got some time to study. Exams on like Friday? God damn. Okay, good luck everyone. Good luck with your studies. And make sure you sleep enough and tune in for tomorrow. All right, tomorrow we'll be dealing with vector calculus, Laplace, and Fourier series. Sorry, no, not to scare you, not Fourier transforms. Okay, you guys aren't ready for that yet. Okay.